request you to, re- install the Cortex software in your computers and practice it. And today we will be discussing about the combinational circuits and how to program combinational circuits in the digital design using the Cortex software and VHDL programming language. Uh, Along with that, I'll also discuss about the project. So the project and how the project you have to do, at what steps you are required to do, and hopefully by end of today you will get it in your emails and in the module as well. Now, first of all, regarding the combinational circuits, hopefully you're getting my screen now. So in the last lecture, we discussed about VHDL. So last 2 weeks we were discussing how to program in VHDL, how to make program, how to make a project there, how to make entity components. So we discussed a lot of things using the VHDL. Now we'll go through the examples of combinational circuits. First of all, what are the combinational circuits we'll be discussing, and then in the combinational circuits, what are the procedures and how can we analyze the circuits. Afterwards, we'll be moving towards the sequential circuits in few weeks, and then we will be discussing different sophisticated circuits along with your project that you will be working on in the lab time. So first of all, the combinational circuits are the circuits which consist of inputs variables and the output variables. So usually the logic circuits in the digital systems may be combinational or sequential. Combinational circuits are the combination of inputs to produce the outputs. So n inputs can be combined together to produce m outputs. Or it's not necessary the number of inputs and outputs should be same or constant. So it can be maybe three inputs, one output, can be three inputs, two outputs. So it depends. M and N values depend on the application and the circuit. So how we analyze, how we get it to obtain the output Boolean function from logic diagram, we proceed as follows. So label all gate outputs. There are functions in there with arbitrary symbols. So first of all, if we have a logic diagram, if we have Boolean expression, we can make its circuit diagram from here as well. If we have uh, the Boolean expression like F2 is equals to AB plus AC plus BC, and the T1, so these T's are the signals. So in terms of VHDL, which we will be discussing for it as well, so T's are the signals and F are the outputs. So, and A, B, C are the inputs. So there are three inputs, and we have three signals in which are produced in between T1, T2, and T3. So signals are in within the system. So our entity, if we say if we need to design entity in the VHDL, it will have in STD logic three inputs and out STD logic that are the outputs that are two outputs here, F1 and F2. And in the architecture, you will define three T1, T2, and T3 as signals. So we have AB plus AC plus BC. So you can directly program it using data flow model. And then T1 equals to A plus B plus C. T2 is equals to A, B, C. T3 is equals to F2 complement T1. And F1 is equals to T3 plus T2. So F1 is equals to T3. So in this terms, you get all these values. However, if you want to design, so in VHDL that will be easier. But structural implementation, classical digital design, if we call. So that is, we have A, B, C. So the signals. So T1, how we are getting T1? T1 is equals to T1 is A plus B plus C. So OR gate of all the three inputs. So A, B, C with the OR gate, we get T1. If you have any questions, please feel free to ask, and don't worry. Inshallah, you will achieve really good in this one. So please ask the questions. So that's T1. And similarly, T2 is equals to ABC. And T2 is, you can see that's ABC. So it's ABC, it's a product gate, that's the AND gate. So the AND of A, B, and C gives us T2. T1, and so T2 and F1 is equals to T3 plus T2. And T3 is simply F2 bar or F2 complement T1. So F2 complement, so and that's, so what is F2? F2 is AB plus AC plus BC. So AB means AND gate between A and B. AC is the AND gate between A and C. BC is the AND gate between B and C. And we are having OR of all these three. So AB and AC and BC and we OR them together, all three, and we get this as F2. So F2 complement means F2 with a NOT gate. So when there is NOT gate, so F2 bar, we get it this AND gate. So T1 times or T1 and F2 complement. So T1 F2 complement. So T1 is there, F2 complement is there. So that's T3, and T3 F1 is equals to T3 plus T2. So OR gate of T3 and T2. So this is T3, that's T2. So when we OR gate, that's very simple. So we get F1. So which one is the structural implementation and which one is the data flow model? What do you think? So there are two implementations in VHDL given here. So if I say you in the project to implement the structural of this, which one you implement? I need answers, brothers, please. See,
Again,
my question is which one is structural implementation and which one is the data flow modeling? As we discussed previously, that there are three types of methods. One is the structural implementation, one is the data flow modeling, and one is the behavioral modeling. So, which are these models? This one, if I want to implement in VHDL, this one, which one is this? And if I want to implement this one, what we call this? Is it structural, behavioral, or data flow? And which one is this? Actually, that one, sorry. So that one is the data flow modeling. When we have Boolean expressions, when we have simply the hardware modeling, so that's the structural modeling. So when you convert this into textual VHDL code, that will be structural model. And if we have truth table for that, that will be the behavioral model, like this one. So in terms of truth table, we have, this is the truth table. So when we wrote the truth table for this, so that is when we implement it, that will be the behavioral model. And we need to involve the process statements and the case statements in those cases, as we did in the examples last week. So there is another example now, that's code conversion example from BCD, binary coded decimal, to XS3 code. What's XS3 code? XS3 code is adding 3 into the BCD number. So when it is 0, it means XS3 will be 3. So if it's 1, XS3 code will be 4. So that we will be now designing the circuit in combinational circuits. So This is taken from Morris Mano's book and chapter number 4 of it. The book is already available to you as a soft copy, I think, in the Moodle, and also available in the library as the hard copy. Input BCD. So we have A, B, C, D, four inputs because BCD code are from 0 to 10, 4 bits. So four digits BCDs are there. So you can see 4 bits are there. And similarly, we have the access codes obviously will be 4 bits as well. So 0000, it will become as access 3. So add 3. So 0011. So when we add 3, 3 is 1 1. So when we add 3, it will become 1 1. And when we have 0001, so it means 1. When we add 3 into it, it becomes 4. The binary number of 4 is 100. So 0100. Similarly, we have all these codes. So this, if we say this is 81000, it becomes 8 plus 3 is 11. So binary number of 11 is 1011. And similarly, that's 9. 9 becomes 12. So 1100 is the binary number of 12, and 1001 is the binary of 9. So using the mapping in Karnaugh maps, we can reduce the expressions which we have taken from the truth table. When we map them in the Karnaugh maps, we get these numbers. And uh, when we so Karnaugh map, as you know, in the digital principles, you have already studied it, that Karnaugh maps are the procedures or graphical reducing the Boolean expressions. So instead of doing using mathematical laws to reduce the equations, Karnaugh maps directly map them and reduce them. So we get z equals to d dash or d complement, y equals to cd plus c bar d bar. If you have any questions regarding Karnaugh maps, please you can discuss with me separately. You can have a meeting with me and we can discuss. I can clear you all your doubts into it. So y equals to cd plus c bar d bar, and similarly x is equals to b bar c plus b bar d plus b c bar d bar, and similarly the w is equals to a b c plus b d. So these are the maps. So now we have these four Boolean equations for each. So we have for w, x, y, and z. When we implement it, uh, we already get this values, and we can implement it in the structural or hardware as similar to this. So z is equals to d bar, so d bar, so d is this one, so d complement or not gate, we get z. Similarly, others are as well. Now coming towards one of the realistic circuits, that's the binary adders and subtractors. You must have heard about them. We are using actually every time, so on and so forth. So the combinational circuits that perform addition of 2 bits are called the half adders. So when we have 2 bits like A and B, when we add them, these are known as the half adder. So when we add two numbers, we have a carry and a sum always there. So even in simple decimal numbers, if you add 3 plus 9, so that will be 9 plus 3 is 12. So 2 is the sum and 1 is carry. Same is the case, same applies to the binary numbers as well. When we add 2 bits, 0 plus 0, it's 0, and sum is 0, and carry is 0 as well. 0 plus 1, sum is 1, but the carry is 0 because there is no carry. 1 plus 0, sum is 1, and there we are not carrying anything from there as well. 1 plus 1 obviously is 2. 2, if you convert it into binary, that is 1 0. So sum is 0 and carry is 1 here. So this becomes the truth table when we add them. So how you make a system, you need to make a logic accordingly. This is a adder, so we are adding the numbers. Any question coming or just a minute? All right, if you have any question, just not only raise, you can directly talk in between. So according to this, when we implement it, we get logic diagram. So this gate is a complex gate, A exclusive or B. From here, you need to take the expression. So what will be the expression for Boolean expression out of here? If we see the Boolean expression will be wherever the ones, as we discussed earlier. So A bar B plus A B bar is for the sum, and for carry it is A B is one. So A B, the AND gate between them. So A B is this. So A bar B plus A bar B plus A B bar is the simple expression for exclusive OR gate. So this is the XOR or exclusive OR gate. We get sum from there. Now, as we our main focus is always the VHDL language. Now, this one half adder is implemented using data flow diagram here. So we should have three parts of the VHDL language. First is the libraries. So we put library. This time I have put more libraries to give you some feeling, but only 1164.al as we were using in previous lecture will be enough for this type of code because it's very simple. But for future words, different tasks that you will implement, you need to have different libraries that you need to explore through the codes. So library IEEE is a simple syntax. Use IEEE dot std logic underscore logic underscore 1164 dot all. Similarly, use IEEE dot std underscore logic underscore arith dot all. So this is another one. Use IEEE std underscore logic underscore unsigned dot all. So these are the libraries. Then we have entity half adder is so a b in. So we can put in bit, but what we have used previously is better. So you can use std underscore logic. So as they are 1 bit only, so in std underscore logic will be better. So similarly some, but this is also possible. So bits, because we are using only the 1 bit, so bit is also available. So in std logic or in bit, both are fine. Some carry as the output. So we have done sum and carry are outputs. A and B are the inputs. So we define them as the ports, A, B as the inputs, and sum and carry as the outputs. So half adder entity. So this is the entity we design. Now in the architecture, here I'm following the data flow. So we need to have their equations. So as we have seen that it's exclusive or A XOR B, and carry is assigned the value A and B. So end data flow. When you write this code in Quartus, you should be able to see the RTL diagram for this as well as the timing waveform for this. So you should be able to go through the timing waveform as well as the RTL diagram. Now, the full adder. The full adder is the complete adder, 1 bit complete adder. Instead of 2 bits, there can be, the carry bit coming from previous bits. So if we are adding, let me give you an example in decimal numbers for simplicity. If we are adding 33 plus 9, let's say, so that will be the first bit. There is no carry. So we have 3 plus 9. 3 plus 9 is 12. So 2 will be sum and 1 will go carry. So if I can write here, let me. So if we have, if I'm saying to you 33 plus 9, so that will be some will we will put here, and there is one carry. So this is our carry. So this 1 plus 3. So this is, and there is no number. If there is a number here, then we will add that as well. So you can say here A is 3, B is 9. In this bit, we have C is 1, B A is 3, and B is 0. So that's 3 plus 1 is 4. So that's the sum, and there is 0 carry as well. So we can have input carry and we can have output carry as well. So input carry is coming from, and output carry goes to the next bit. Now, if we add these three, so this is A plus, so A plus B plus C in, so 0 plus 0 plus 0 is sum is 0, and obviously the carry is 0. A plus B plus C, so 1 plus 0 plus, so it's 1, so sum is 1, carry is 0. Similar is the case this one, sum is 1 and carry is 0. In this case, 1 plus 1, its sum is 0, carry is 1. 1 plus 0 plus 0, sum is 1, carry is 0. 1 plus 1, carry is 1, sum is 0. So 1 plus 1, 2 means carry is 1, sum is 0. 1 plus 1, 3 plus 1, 1 plus 1, 2 plus 1, 3. So 3 in binary is 1, carry, and 1 sum 11. So this is our outputs. Now we need to design it in VHDL. So in VHDL, now we will design this. So first of all, what we do using Karnaugh maps, we have reduced it. So C out is AB plus AC in plus BC in. C in is the input carry and C out is the output carry. For some, there is no reduction because there are no adjacent cells. So A bar, B bar, C in plus A bar, B, C in bar plus A, B bar, C in bar plus A, B, C in. So that's the exclusive OR gate, and we have for carry AB plus AC in plus BC in. So this will, we will add them as this is the equation: AND gate, AND gate, AND gate, and the OR gate between them. So AND gate, AND gate, AND gate, and the OR gate between them. So get the C out. Now this full adder circuit using data flow modeling first of all. So now we have three inputs, so we need to have entity, full adder. I have not written one thing than previous code. Could you tell me what's not written here, what I have missed in this code? Something other is written which is not written here. What do you think, what's that?
The library IEE and the
Correct. Very nice. Very nice. So the libraries are missing. So because but for you, you need to write when you're writing the code, you need to write the libraries. Here, I'm only, giving you understanding. So libraries will be same as the previous ones. So here I've given it name as full adder. So full adder, whatever name you can write, full adder complete, you can write adder, whatever you want to write, you can write accordingly. But entity is, these are the keywords. Port is a keyword. Here, as I was telling you, bit, instead of bit, I have written the std underscore logic, which is more over the used thing, and it should be used. A B C in, so these are three inputs. You can see we have three inputs A, B, C in. So these are the three inputs, and we have outputs which are sum and C out. So we got sum and C out. So out std underscore logic and full adder. So that is our entity. Now architecture. We have exclusive OR gate and we have AND gates with the so we write the data flow of, I've given it name as data. So architecture is a keyword, of is a keyword, full header for which for what we are writing this architecture or method, we are writing it for this entity. So we put the name of the entity is, so data is the name of the architecture and full header is the name of the entity. And begin, so we begin the architecture, we write sum is assigned value of a exclusive or b x or c in. So a b c in with exclusive or we get the sum. And similarly for carry out, c out is our output. So c out we have a and b. So we have the inputs a and b. Here we have used a and b, so that's the AND gate. Or B and C in. So B and C in is this one. Now this one is left. So that's AND or C in and A. So C in and A is this gate. So we have used, and at the end the exclusive, oh sorry, the OR gate between them. So this gives us C out. So this is the data flow model for the uh, full adder. Now, if we move to behavioral model, now behavioral model, same entity. So I've put here the, the library files to give you the understanding. Now here the entity full header. So we have A, B, C in same sum out. So you can see it is same entity, but I've changed its name. Full header behave. So I've given full header behave be as the name of this entity because I'm designing behavioral. So that I should distinguish between when I'm going through these modules. So the entity name I have changed here, so it's a separate project. Obviously, I want to compare the results. Then architecture behavioral of full header is full header behave. So that's the entity name. Behavioral, I've given the name to this architecture is a keyword. Architecture is a keyword. Now here I'm using signal ABC in 2 down to the 0. So this is a 3-bit STD logic vector. Why I'm using this? Because I want to concatenate 3 input bits together for behavioral model. So ABC in is assigned a value A and B and C in. So this is not AND gate. You can see AND gate previously we used. This is the AND gate operation. This is the operator which is used to concatenate. So it first bit and second bit and third bit of this vector, as we have defined it as a 3-bit one. Signal ABC in. So A and B and C in, they are now, this is the first bit, second bit, and third bit. Now we have 000. So all those values, where are we getting from? Behavioral is, as I told you, from the truth table. So it should have all the 8 values. So you can check all the 8 values are there, 000, 001 till 111. So sum is 0. So all the outputs were of the sum. Similarly, we have the C out for it as well. So this is case. In C or C++, we use switch and then case. But here in VHDL, we need to use first of all the process ABC in. We are doing process on this begin and case. So case is like switch statement, as I was telling you. ABC in is when it is 000. So 3 bits which we concatenated here or combined them together here, and then sum is 0 and C out is 0 according to the truth table. You can check. So when these are 000, sum is 0, carry is 0. So that I used here. So sum is 0, carry out is 0. Similarly, for all those values are taken from the truth table. End case, because that was we are started the case here. So end process and then end behavioral is the name of the architecture, so we are ending the architecture here. So 2 methods so far we have discussed. First method is The data flow model, very simple. So you can just write it down. And similarly, here we have the uh, concatenation. So this is the behavioral model, and at the end we have the structural modeling, where we are doing the same a half adder. So half adder, two half adders, and OR gate, we get it as the uh, you know uh, the full adder for this. So this is the full adder which we are designing. So full adder, port ABC in STD logic, same entity. Behavioral, now I've put it as behavioral here. So it's up to me. But it should be, I should have put it as a structural for my understanding, that I am using it as a structural component half adder, which I already defined in my project as a single entity earlier. This one. So this is half adder separate file, and the second file which I am designing, that's this one, where I'm defining it as the component half adder port XY in STD logic. So XY. So here I'm port mapping, as we discussed in previous, that how the structural modeling can be port mapped. So L1, L2. So first level of the, or half, first half adder, second half adder is this one, and we do C out temp 2 temp 3. So temp 2 temp 3 C out is this one, and these are the carries. So entity full letters, some. So this was the structural modeling with this given, and C out is temp 2 or temp 3. So temp 2 temp 3, and sum is the end of these two. Okay. So further it is implemented for you guys. So now what you have to do, the assessment, which or one exercise, repeat all the things which today I have given to you or explained to you, the half adder, full adder. Now I want you to design half adder using structural modeling, and half subtractor and full subtractor. So you need to do behavioral and structural design for half adder, half subtractor, half full subtractor. So subtractors I haven't discussed in this lecture, but I want you to go through the subtractor logic and design it in VHDL using the structural design as well as the behavioral design. At the end, on the performance, there is no difference, because these are the methods, different methods of implementing the circuits. All right. So this was the lecture, and now if I move further to the important aspect, that's the project for digital design this semester. Now, as I explained you, the project, that what the marking criteria, that's the 75% is the report and 25% is the presentation. So it's a group project, report and presentation, and the deadline will be 30th April. So you need to submit by 30th April to us. There are two sections given in this project. First is in, so I'm reading it so that whatever there is, you can understand very well, and then I can explain you or we can discuss. In this task, you are required to design an electronic dice game. So you are required to design a dice game as shown as this block diagram. So this is the dice game given in this block diagram. I will record a separate explanatory video and put it on the Moodle as well. So this figure one is explaining the dice game. It has two counters, 1 to 6 in which two counters are employed. So these are two counters to simulate the roll of the dice. Each counter counts the sequence 1, 2, 3, 4, 5, 6, and repeating 1, 2, 3, 4, 5, 6. So obviously, the dice is 1 to 6. So 1 to 6 counter and then repeating itself. So we have these two counters. Now, so after dice roll, the sum of values. So we have two counters and there is adder, as we did the adder we have done in today's lecture. So you need to add these values to get the sum. So the sum of values in the counters will be in the range 2 through 12. Obviously, 1 plus 1 is the minimum value and 6 plus 6 is the maximum value. So it will be from 2 to 12. The sum will be from 2 to 12. And point register we have, and that from the sum we get a point register and we get a comparator, that's the test logic. So we have these conditions are there. So we need to consider these conditions for winning. So test logic will test the logic according to these conditions. The player wins if the sum is 7 or 11 after the first dice roll. If somebody gets the sum as 7 or 11, then he's the winner. However, if the sum is 2, 3, or 12, if the sum is 2, 3, or 12, so 2, 3, 12, then he loses the game. The player loses the game. So this is the first rule: 7 or 11, winner. 2, 3, or 12 is the loser. Else, the sum obtained on first roll is referred to as a point in the point register. So if it's a different value, then it is going to the point register. So if it is, for instance, it's 4, so it will go to the point register. 5, it will go to the point register. Then what will be done with the point register? As the player must roll the dice again until the result of the game is decided. So the person who's getting into the point register need to roll the dice again on the second or subsequent rolls. So what happens in the second or subsequent rolls? The player wins if and only if. So there is only one condition: if sum is equal to the point value stored in the point register. So sum is equal to the point value, and if the sum is equal to the point value, if it was 4, so sum should be equal to point value, then he is the winner. If or loses when the sum is 7, or if it is 7, then he loses now. Otherwise, player rolls again and again. So whether if the value should come same as point value or point register value, then he's the winner. If it is 7, then he's the loser. Otherwise, so you're required to design algorithmic state machine for this. So we will work out about ASMs. So for the above described dice game and then implement it in VHDL. So you're required to design it, um the ASM for this, and implement it in VHDL. The second question is the GCD. The greatest common divisor of two non-zero integers is the largest positive integer that divides each of these integers with a zero remainder. Figure 2 shows C program segment. So C program segment is given temp A, temp B. So what is GCD, greatest common divisor? This is a mathematical implementation. Go through that. I will explain in a separate recording. So while temp A is not equals to temp B, if temp A is, so this is the algorithm for GCD given to you. So you need to use this algorithm, and in this task you are required to understand Euclidean algorithm to compute GCD and design a digital logic circuit in VHDL that computes GCD of 2n with unsigned integers. For instance, n can be taken equals to 8. Prior to that makes sure understand the basic algorithm for calculating GCD of two numbers. A suitable data path for this is also given to you. So the data path is given to you for this. So that's the simple processor data path for this is already given to you. You need to use this and design this. When the two n-bit unsigned integers are set as x and y inputs, then the start signal is enabled and you compute the GCD. So uh, note that once GCD computation is started, a new calculation cannot be started until it is finished or reset. So it is also 50 marks. So both these tasks or section 1 is 50, section 2 is 50. So they are contributing equally into your marks. Now marking scheme, what you need to submit in the report, it should be according to this marking scheme. Program design approach and description, how you are designing the program, what type of, so your approach to this, what type of methodology you are using, you need to put the flow chart for that. So and you need to describe the sections of your program, so that's 15 marks. Well commented program, include program and function banners. So your program should be well commented and it should explain every step in the code. So it shouldn't be just a written code, but it should be very much explanation of the code should also be submitted. So it's 25 marks. RTL and typing waveforms and discussion in the report. So discussion on the results of RTL and typing waveforms is 10 marks. So overall it becomes 50% marks. Similarly, for the section 2, that's the GCD, same three steps, but they have different marks. So program design approach and description, here you need to use different, here you are required to use the ASMs. Here maybe some other flowchart type, so you need to go through this and do that. So that will be 20% marks. Similarly, well commented program include program and function banners, as I explained. So similar thing, it has 15 marks, and the discussion on results, timing waveforms, and RTLs is 15 again. So that's 50 marks. So that's 100% report marking. For individual assessment, you will be given the individual contribution form on Moodle. It will be shared with you, where you will be required, to honestly let us know who has worked how much. So if some person if there are two people in the group, and if one is person A is working 60%, so he will be 60%. So this is how it is calculated. So from this formula you can work it out. So maybe 1 or 2 marks for a person who's working better to get the better mark. Obviously, the both of the members of group or three members of the group can be together and should work in a better way. So presentation that includes complete demonstration of the work completed carried out in the project assessment. Individual student contribution will be assessed during the presentation. So in the presentation, as I explained earlier as well, you will be asked questions separately. It's not from uh, any desired portion, but from all the project. So we can ask you questions from anywhere from the project to assess you. The presentation shall or schedule will be announced during that time, and there is a late policy of 48 hours uh, according to UV, and we will consider that. Anything regarding groups, let me let you know. The groups can be here. I've only explained about the groups, but groups can be 2 to 3 members. Uh, it is given in the module specifications, so we cannot have more than 2 to 3 people in the group. Any questions you have, please do ask me.
Yes, Mr.
Yes.
About the presentation. About the presentation, it will be after submit the project or with it or how? or before?
Yes, yes, Sohail, it will be after submission of the project. I will announce the dates. So full schedule will be announced to you, and you will present accordingly. So it is in the first or second week of May, because this deadline for project is 30 April. So after 1 or 2 weeks, but you will get it before, much before. Maybe around 15th of April, you will get the schedule. Okay, so I will try to give you. It should be face to face, but if permitted, I cannot promise you at the moment. If it is permitted, we will allow you online presentations. But you all need to attend, because you know question answer session is separate to each person. Okay. Any other question? All right. So I will, inshallah, release the assessment, inshallah, by today. And best of luck, inshallah. You'll It's not, it's challenging and understanding, but it is achievable, and many people get a good grade in digital design in similar type of assessments. All right, brothers. So, and have a good time. Please pray for yourself, pray for me in during these important days of Ramadan. Inshallah,
Inshallah.
see you. Assalamu alaikum warahmatullah.